All right, so we're going to take a look at significant figures. And it's interesting, significant figures aren't as significant as they were probably in your Chem honors class or your AP Chem class. So it does matter, but we do not spend a lot of time talking about precision. So let's just take a few quick examples and look at this, and you'll see as the year goes on that you don't get questions on the AP exam about significant figures, and you won't lose points in my class because of a significant figure answer if you're off a digit or something that's related to you missing a problem, an answer to a problem because you didn't get the significant figures right. So let's look at a few of the rules here. Let's say you're multiplying two numbers and the first number has three significant figures and the second one, 5.7, has two significant figures. The product of that, when you get the answer, you use the lower of the two significant figures that were used to get it. Now, what does it mean by least precisely known number? Let's say you wanted to measure a pencil and you had a ruler that had centimeter increments, 1 centimeter, 2 centimeter, 3 centimeter, didn't have all the little small millimeter, the 10 in between the centimeters like you see it on rulers at school. So you put down your pencil and you notice it's between the 10 and 11 centimeter mark. And you're like, well, there's no small little degradation, smaller gradations where I can figure out where exactly the measurement should be. But I notice it's halfway between the 10 centimeter and the 11 centimeter. So what you'll do is you would probably say, oh, my pencil is 10.5 centimeters in length. So that 0.5 that's between the 10 and 11 that you estimated, that's your least precisely known number because you estimated it without having a mark on the ruler to use. That's what it means by your least precise known number. All right, so if you're adding or subtracting, what you do is, again, you can see on this example, 106.6 is not as precise as 18.54. That 4 makes that measurement a little more precise. So when you add numbers like that together, you actually have to go with the least precise of the two. And so you line up the decimal places, and you can only go to the tenths place for this. Exact numbers, where it has here, it says number 3, exact numbers have no uncertainty, and this is when we're talking about pi or the number 2, so we don't have to worry about significant figures with those. Those are exact numbers. We're using those. And the little red box at the bottom, where it says it's acceptable to keep 1 or 2 extra digits during the intermediate steps of the calculation. I'm not really too concerned about that. There's a setting on your calculator where you can go with a floating decimal point, or you can pick how many decimal places you want. So let's say you want to go 2 digits behind the decimal place, 3. There's choices for that. I think my calculator, I'm going to look right now at this moment, and I have it in floating. So I hit mode, and the second line down, it says float. So I have it in floating. That's good enough for me. And as you'll see as the year goes on, it will not play a major role. All right, so anyway, scientific notation does play a major role. Physics is a science class, and we use the powers of 10 constantly, all the time. So you'll be using the power of 10, and we'll take a look at like the diameter of the Earth. Instead of having all these digits in science, I mean, what a pain. We make it easier on ourselves by using the power of 10, and then that 6.37, that tells us how many significant figures there are in that measurement. And then go below to something really small like a red blood cell, the diameter of that. No one wants to write 0.00000, and teachers don't want to look at that either. We don't want to see all those zeros. And so the nice thing is scientific notation, it's easier to look at, and also gives information as far as the number of significant figures in that measurement. Is for the red blood cell, 7.5 is the number of significant figures for that. All right, so conversions. Conversions is the thing that students need for conversions. You need prefix tables. And the prefix tables are either found in the front flap of the textbook or the back flap of the textbook. The textbook, we're currently using the Knight college physics textbook. It's in the front flap of the textbook. So if you look up there, you'll see kilos 10 to the 3, centis 10 to the negative 2, micro is 10 to the negative 6, mega, which is a capital M, is 10 to the 6. So you don't have to memorize that. You shouldn't memorize that. You can get access to it. And while you're at it, you want to consider if you have a phone and you can get apps. There's a free app out there. It's a conversion app, and it's very nice because you could do your conversion problem and then you can go into your app and punch in the numbers and see if you got it right. A good way to check. All right, so here's a practice problem. All right, so which one is moving the slowest to the fastest? So it says the smallest to largest. This is called a rank order problem. So we have something moving 1 millimeter per microsecond, 1 kilometer per kilosecond, and 1 centimeter per millisecond. So I have the prefixes written on the bottom for you. I got them from the front of the textbook. And here we go, 1 millimeter per microsecond. So for milli, I know it's 10 to the negative 3. So I just put 10 to the negative 3, and then I put meters on there because we're still using the MKS system here in physics. So M's for meters, K is for kilograms, and S for seconds. We haven't gotten to kilograms yet. We'll get into that when we get to forces. Microseconds. So micro is 10 to the negative 6 seconds. So that's essentially saying the same thing as what you're seeing to the left with the Greek letter mu, microseconds. It's the same as 10 to the negative 6. So now we have numbers, and we can put them to work, and then there's the speed. So I did the next two, and as you can see, the probably the really small whatever, it could be a microbe moving across a petri dish, is moving the fastest, 1 times 10 to the 3 meters per second.